Okay, to find the area of the inner loop of the limacon, so just finding this area in here. Again, you maybe want to look back, but remember area is always 1/2 the integral of r squared. So the easy part is to start off, you just say, all right, it's 1/2 the integral of r squared d theta. Now I actually need to figure out what angles enclose this thing. Okay. Now if I plugged in, let's say, and I always recommend, at least when you're starting, plugging in some points. You know, if I plugged in 0 for theta, for the sine of 0 is 0, 4 times 0, so 2 minus 0 is 0. So at 0, we're right here. This is theta equals 0. So it must kind of track along here, so I'm going to have to find out what angle starts that limacon, and then it'll come around this way, and I got to figure out what angle ends the inner loop of the limacon. So how I might do that is I might set my equation equal to 0. And the reason I'm choosing to do that is because r, remember, is my distance from the origin, and at the spot where the dimpled line, where the inner loop begins and ends, r is equal to 0. Okay, so r equals 0 here because r is a distance from the origin. So then I could solve. So we're essentially looking for where sine is 1/2. Well, that occurs at pi over 6 and 5 pi over 6. So this is the integral that would find the area of just that inner loop. A more interesting problem might be finding the area of the outer part. How you would do that is maybe integrate, half of it or something. Maybe integrate from 5 pi over 6 down to this spot here, and then subtract out the inner loop. That might be kind of an interesting problem. Now, the area inside of the dimpled limacon and outside the circle. So the area that we're talking about is, if I could kind of shade it lightly, inside is here, like that. And that's the area we're talking about. Now, I always recommend with something like this, drawing a line from the origin to the point of intersection, like this. And then over here as well. Okay. And we have to figure out where those two things intersect. Let's figure out what those angles are. So 1 plus cosine theta equals 3 cosine theta. Well, if I subtract a cosine from both sides, I have this. So I'm really looking for where cosine is 1/2. Cosine is 1/2 at pi over 3. And I'm going to put pi over 3 over here. And I'm not going to worry about the -1 quite yet, because I think we could actually just double our answer. Maybe that would be easiest. Now, this spot right here is going to be, for at least the dimpled limacon, this is going to be pi. Okay, so if I integrated my dimpled limacon, let me do that, 1/2 the integral from pi over 3 to pi of 1 plus cosine theta squared d theta. Okay, let me just shade what that would be. Okay, that's what I just found. Okay, and remember, one of the best things I ever heard was think about it like it's a windshield washer. So starting at pi over 3, it just sweeps through, and all the area enclosed is shaded. Well, that means that I need to subtract out part of the circle. So let's try and find that area next. So I'm going to have still a 1/2. Still going to start at pi over 3. And we're going to have 3 cosine theta squared d theta. But this spot in the circle is actually pi over 2. And check that if you don't quite trust it. Cosine of pi over 2 is 0. 3 times 0. That's that spot in the circle. So it's kind of a different a look at this, is that the bounds are different. In the Lymecan, pi over 3 to pi sweeps the shape we want. But in the circle, it's pi over 3 to pi over 2 gives us this. If we went to pi, we'd go all the way back over here, which isn't what we want. So you got to be careful and think about what angles actually give us the part we want. So that would shade this, so then we would find the difference between the two, and that would give us the area we're interested in. And of course, at this point, you would double your answer. You know, maybe I'll just make a note here that you would take this entire answer and double it to get the total area, because we've just done the top. So doubling it would also give you the bottom. I think using the symmetry is important, especially in polars, and this situation shows it maybe even more, because pi over 3, and if it, I kind of skipped over this. I said, well, pi over 3 would do it. The other time that cosine theta would be 1/2 is 5 pi over 3. Which 5 pi over 3 is this location in the Lymecan. But 5 pi over 3, here's what would happen in the circle. It would come down, it would go all the way back around, and then hit 5 pi over 3. That's not what we want to have happen. We don't want to trace the circle a time and a half. So I think it's vital that you use the symmetry in this problem.